Now let us look at the subtraction operation. Okay. So subtraction operation, we use a trick there for 2's complement format, and all the computers, modern computers, uses 2's complement format, and we have already discussed that in our binary number representations. So 2's complement format, there is no need for additional subtraction circuit. Why? Because what we say, your subtraction is nothing but an addition of a negative number. Okay. So let's say I have two positive quantity A and B, and I am subtracting B from A. That means I am doing an addition of minus B from A. So as long as I have this representation, conversion from quantity B to its minus B, I am okay. So what I am saying is, let's say I am talking about A minus B. So this is nothing but A plus minus B. And let's assume A is greater than 0 and B is greater than 0 as well. Okay. In this case, if I can represent minus B in a convenient way, or convert a bit pattern of B into minus B bit pattern, then I am done. I can use an addition circuit here, right? So, which is supposed to be very easy for 2's complement representation. Minus B is nothing but logical B invert plus 1. Okay, logical B invert plus 1. So you see, what we are doing here is nothing but making and transforming the A minus B problem into an addition problem, where assumption is both A and B are in 2's complement format, which is true for any computer in the world today. And then it is an inversion operation of individual bit of B, and then addition of one extra, right? So what we can do, we can pick up our daisy chain circuit, ripple carry adder, where we want to convert B bits of this register B, right? All the bits of this register B going through inversion gate, so it becomes B bar is feeding into my addition circuit, and my first carry in, default carry in, is 1. Okay. So remember, like in our adder circuit, I had a default carry in of 0. Now since I need to do A plus inversion of B plus 1, this plus extra 1, we are doing it through the carry bit of the first full adder stage at the LSB side. Okay, so we are first default carry in is 1, and we are deploying inversion circuit into those full adder circuits. Now what shall we do to now combine this adder and subtractor? So we don't want to deploy like 32 daisy chain connected full adder for addition operation, and another 32 separate 32 chain daisy chain for the subtraction operation, because it will increase our cost of the ALU. So can we somehow combine this subtractor and addition together, adder circuit together? One way is, of course, we all know multiplexer, right? So only what we are trying to do here. If it's a subtraction operation, I need B bar. If it is an addition operation, then I need B, right? One is complemented from, uncomplemented from, depending on the operation. So, well, I deploy a multiplexer. Okay, multiplexer is choosing between my inverted bit or the or I say complementary bit in terms of logic, or the uncomplementary bit of the logic, depending on selection bit is 1 or 0. And this selection bit, I can say that, let's say I have input of S and A mark. This is a name S and A, where if I set this S and A to 0, it's addition, if I set this SNA to 1, it's a subtraction. How? First, let's understand what is this like connection between one marks to another mean. Okay, it does not mean, please like listen this carefully. This does not mean one output coming into another input of the marks. This is not a daisy chain connection of the. This is not a daisy chain connection of the multiplexer. What it simply does is a simplification of the schematic diagram, which says my SNA is connected as a selection circuit for all the masks. Okay, so this SNA this is a selection terminal, let's say, for the multiplexer, 2x1 1-bit multiplexer, and this same SNA goes to selection of mask 1, mask 2, mask 3, and mask 4. Okay, that's what this daisy kind of connection represents here. Okay, so don't mix it up with like some of the output, another output coming out apart from the selection and going into another marks. It is not. Okay, this is simply same selection lines, the selection inputs of the multiplexer is connected to the same control signal SNA. And now let's see, like as I defined by this logic, that if it is 0, SNA is 0, it's addition. So this multiplexer will select my uncomplemented form of the bit and feed into the daisy chain of this ripple carry adder. Whereas if it is set to 1, then it will pick up the complementary form of the B, right? That means in the subtraction mode. Now that means SNA is 0 is addition, SNA 1 is subtraction, whereas in the carry in, what should I send in? For the addition, I need to send in 0 for the first full adder carry in. For the subtraction, I need to send in 1 for the subtraction operation, right? 1 for the subtraction operation in the first stage of the full adder. This is same as is your SNA bit. So same SNA bit is connected to the first full adder, 1-bit full adder carry in as a default carry in of this circuit. It's well fit because SNA set to 0 is addition. So I am feeding in 0 into default carry in for the first full adder. If SNA is 1, is a subtraction, and I am supplying the same 1 into the default carry in for the first full adder circuit. Now question is, you know how the multiplexer inside looks like, right? It has a decoder, it has this last stage of AND. It's a lot of gate. Multiplexer is big circuit. Can we optimize on top of that? What I say, yes, I can. What we simply need to do, replace all this multiplexer and inverter circuit that we showed here conceptually with simple XOR gate, where one input of this XOR gates coming from the register different bits B0, B1, B2, B3, and another input are connected, all of them connected to this SNA signal. Now how does it work? Okay, let's work it out. So what I want to say, like SNA and let's say I'm talking about some like bit B0, okay, and let's say the B is what going into ripple carry adder addition circuit. Okay, so if I can say that if it is addition, if B is 0, this should be 0, 0, 1, this B is 1, 1, this is mean subtraction, I need to get B0 is 0, I need to give invert of the B0, right? So it will be 1 and 1, 1 is 0. Now look at this truth table. Isn't it an XOR? B is nothing but S and A. Okay, I cannot do that circuit here, like symbol here. Okay, this is XOR between B0. Same thing, you do it for the B1 and B2 and B3 and B4, right? So that's why we can replace the whole multiplexer and inversion combination of the circuit with simple XOR circuit. Okay, and that becomes your final simplification adder subtractor circuit with somewhat simplified form.